Hello everyone, and welcome back to the Fluctus Channel. It is one of the most dangerous aircraft most pilots will ever operate. Yet for 70 years, it has remained the backbone of the US spy machine. In the early days of the Cold War, Lockheed Martin began developing a surveillance aircraft capable of flying higher and farther than any other, the U-2 Dragon Lady. However, because this aircraft can reach altitudes of 80,000 feet, pilots and ground crews must go through extensive preparations. To evade enemy sensors, missiles, and other defenses, the U-2 must operate at the very edge of space. Functioning at such heights requires pilots to complete an intense preparation process, both physically and mentally. For this reason, their mission begins hours before they even step into the aircraft.
So last night had steak and eggs, about 17.
U-2 pilots not only modify their diets, but also wear specialized heavy flight suits. Once suited, attendants equip them with multiple layers of gloves to protect against the freezing temperatures. The specially designed helmets supply oxygen, which pilots breathe for at least 1 hour to purge nitrogen from their bodies, preventing decompression sickness at high altitudes. Even before World War II, pilots and engineers understood that the human body could not function beyond certain altitudes. The combination of extreme cold, limited oxygen, and decompression sickness meant crews required protective equipment. What began as simple oxygen masks gradually evolved, incorporating elements from the ongoing space program. In fact, the modern U-2 pressure suit is directly descended from those worn by Apollo astronauts.
Reach for the ejection handle and then use your dominant hand to push down.
Although these suits are life-saving, they are also bulky and restrictive. Due to limited mobility, pilots need assistance from several ground crew members throughout the pre-flight process. After completing oxygenation, pilots are transported to their aircraft while carrying a suitcase filled with oxygen. Ground crews then guide them to the plane, assisting them into the U-2's cramped cockpit. Once secured in place, the oxygen suitcase is removed, and the pilot is connected to the onboard oxygen system. Ground crews conduct final checks before sealing the canopy. The pilot is now prepared to undertake one of the most demanding flights imaginable. The U-2 was engineered for long-range flight. As a result, its designers equipped it with long, glider-like wings that extend more than 40 feet beyond the fuselage. To further minimize weight, the U-2 lacks conventional landing gear. Instead, it uses a bicycle-style configuration, with a single wheel at the front and another at the rear. For balance, temporary pogo gears are attached beneath the wings to support the aircraft during taxiing and takeoff.
Take the load off. Appreciate you.
To enhance safety during takeoff, a designated chase car follows the U-2 along the runway, providing real-time guidance to ensure a safe departure. Although the U-2 is officially rated for 70,000 feet, or 13 miles, it is believed that under certain conditions, it can reach around 80,000 feet. At this altitude, pilots can see the curvature of the Earth and even glimpse into space. From this vantage point, the U-2 remains beyond the reach of most countermeasures, while gathering valuable intelligence from across the globe. Landing the U-2 is often considered the most challenging phase of the mission. Due to its lightweight structure, the aircraft is difficult to control at lower altitudes. Once again, a chase car assists by relaying information about altitude and approach angle. After touchdown, the aircraft's large wings cause it to tip to one side. The pogos must then be reattached so the aircraft can taxi back to the hangar. The reason pilots, ground crews, and the Air Force accept the challenges of operating the U-2 is its exceptional reconnaissance capability. One of its most powerful tools is the optical bar camera, a long focal optical system designed to capture panoramic images from high altitudes. The camera onboard the U-2 can produce high-resolution images of terrain, cities, and military installations in a single pass. Aside from the engine, the OBC is among the largest and heaviest components of the aircraft. Over the years, it has played a crucial role in intelligence gathering, especially in monitoring enemy facilities and tracking troop movements. It also serves non-military purposes, including scientific research, atmospheric data collection, and environmental monitoring. At Beale Air Force Base in California, the 9th Intelligence Squadron employs specialized aerial imagery production technicians who process the footage captured by the U-2's OBC. Once a mission is completed, the real effort begins on the ground. The large negatives captured by the aircraft's cameras must undergo careful processing, with technicians enhancing details and identifying critical intelligence data. The final images are printed and examined closely, as specialists search for even the smallest anomalies that could indicate missile silos, aircraft activity, or concealed bunkers. This meticulous process provides the U.S. Section, military and intelligence community, with vital insights that influence global policy in both wartime and peacetime. Despite its fragile appearance, the U-2 is a durable workhorse, with many airframes logging thousands of mission hours. Like the pilots who operate them, The Dragon Ladies endure significant stress due to the extreme altitudes at which they fly. For this reason, they require regular disassembly for maintenance and upgrades. Taking apart a U-2 demands specialized technicians familiar with its unique design. Because Lockheed Martin prioritized weight reduction, the aircraft features a modular structure, allowing the engine to be removed from the fuselage as a single unit. This provides technicians with easy access to inspect components for wear and damage. During maintenance, the entire aircraft is stripped down, tested, and reassembled to ensure it remains ready for its next mission. Any components that fail inspection are either replaced or rebuilt. At the core of the U-2 is the General Electric F-118G 1.1 turbofan engine. This powerful yet efficient engine enables the aircraft to maintain high-altitude flight, producing up to 17,000 pounds of thrust. Unlike other reconnaissance aircraft, such as the SR-71, the U-2 was not designed for supersonic speeds. Instead, engineers focused on maximizing endurance. Testing plays a crucial role in maintaining engine performance. During these procedures, technicians place the engine inside a specialized test facility and operate it at different power levels, checking for irregularities, leaks, or mechanical faults. Even after 7 decades of service, the U-2 Dragon Lady continues to be a key component of the U.S. intelligence network. Much of its success is due to the maintainers who ensure every part is regularly inspected, tested, and replaced when necessary. From ground crews responsible for refueling to those conducting pre-flight inspections, everyone involved with the U-2 undergoes extensive training to ensure proper qualification. These technicians work tirelessly to keep the aircraft in optimal condition, especially during field operations. They understand the vital role the U-2 plays and will continue to play for many years to come. Through their dedication and expertise, the Dragon Ladies of the U.S. Air Force will keep soaring at high altitudes. Space exploration has driven the creation of new technologies, leading to innovative vehicles capable of traveling beyond Earth's orbit. One of the primary goals in this field is the development of reusable spacecraft that can launch into space and return multiple times, making missions more cost-effective and encouraging more frequent exploration. This has led to the development of spacecraft like the Boeing X-37 since the early 2000s, designed for orbital experimentation, technology testing, and long-duration research missions. The vehicle is the first since the space shuttle capable of returning experiments to Earth for detailed examination and analysis. To place the X-37 into orbit, powerful launch vehicles such as the SpaceX Falcon 9 or the Atlas V from United Launch Alliance are required. Both rockets have been used to deploy the X-37 during testing and operational missions. Typically, the spacecraft is enclosed within the rocket's payload fairing, an aluminum shell with thermal protection located at the top of the rocket. Once secured, the rocket is transported to the launch pad using a crawler transporter, a massive tracked vehicle capable of carrying heavy loads. At the launch site, control systems are connected to the propulsion systems that engineers manage during ignition. Years of testing and repeated launches have enabled engineers to refine and enhance the spacecraft systems, resulting in longer missions and more ambitious goals. Since 2010, the X-37 has completed 7 missions, accumulating a total of 4,010 days in orbit, often testing experimental payloads, spacecraft durability, and small satellite deployment. However, reaching orbit is only part of the mission, as re-entry and landing are equally critical due to the risks involved. This is why its design draws from space shuttle technology, incorporating a thermal protection system made of silica ceramic tiles. Equipped with advanced avionics, the spacecraft can re-enter the atmosphere and land like a conventional aircraft. The X-37 has demonstrated its capabilities by supporting various experiments conducted in orbit. Each launch provides an opportunity to test and evaluate new technologies, such as the photovoltaic radio frequency antenna module. This experiment aims to capture solar energy in space and convert it into usable power that can be transmitted back to Earth. Continued testing could lead to a consistent and reliable energy source unaffected by atmospheric conditions. Collaboration across multiple sectors will be essential to overcoming the challenges associated with these and other experimental technologies. From the edge of space to orbit and back, these platforms represent the forefront of surveillance and aerospace innovation. Whether it is the U-2 quietly collecting intelligence at extreme altitudes, or the X-37 advancing the limits of reusable spaceflight, both highlight how precision engineering and human expertise continue to shape the future of aviation. As technology progresses, these systems will remain essential tools, expanding our reach, deepening our understanding, and ensuring mission success both in the skies above and in the vast expanse of space. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.